Sorry about that. We had a little technical difficulty, and for some reason the camera stopped recording, and I can't see it, so I didn't know it. So we're going to take two here. So if we're looking at this problem right here, where we calculate the volume of 1 mole of a gas, but notice it's at STP again. So since it's at STP, I know that I'm going to use the 22.4 in there. I have the mole, I have the pressure, I have the temperature, so I'm looking for volume. So the only thing I need is the volume. I have everything else. So in PV equals nRT, I know the pressure, I know the volume, but pressure has to be in atmospheres. Moles is given as moles, R is always 0.0821, and temperature has to be in Kelvin. So we just plug it in, and then you can just kind of solve for it. And it's super easy, and just note, again, it comes out to 22.4 liters, okay? So 1 mole of a gas at STP occupies 22.4 liters. This is a huge, huge concept, okay? Because this is 22.4 liters. So if I had this down to 0 degrees and this normal atmospheric pressure, I would know that there's 1 mole of a gas in here. Now that's huge, okay? Because Avogadro's principle said equal volumes contain the same number of molecules. The converse of that is equal molecules will occupy the same volume. So 1 mole of any gas is always going to be 22.4, but that is only true at STP. Okay, so but whenever you see something at STP like this, we're going to know that we can use the 22.4 as a conversion factor for us. Okay, now STP, you got to know STP is always 1 atmosphere, 0 degrees Celsius, but we always have to do Kelvin, 273 K. Okay, and 1 mole of any gas is always going to be 22.4 liters. That's tremendously important. That has to just ring true. If you're at STP, you have to think of the number 22.4. Okay? Now, once I have that now is a conversion factor between liters and moles. And you know with conversion factors, you can set them up either way, whether you multiply or divide. Okay? But liters always goes with the 22.4. There's not 22.4 moles in 1 liter. It's 22.4 liters is 1 mole. Okay, so we can set it up either way, but always keep the 22.4 with the liters. And we'll use that in stoichiometry a little bit later on here in just a second. Okay, so if we know 3 of the 4 variables, we can go ahead and solve for the 4th one easily, just plugging into PV equals nRT. What makes these problems different is that you only have 1 volume, 1 pressure, and one temperature, and moles is given. Okay, only 1 set of conditions. On Boyle's, Charles, and Gay-Lussac's law, it's all going to be about 2, given initial pressure and a final pressure, P1 and P2, V1 and V2. Here, we just have 1 set of conditions. That's my first clue that I'm going to use PV equals nRT. The second clue is I'm given moles. Moles doesn't work in Boyle's, Charles, or Gay-Lussac's law. So I know that I'm going to have to just plug in. I know my volume, I know moles, I know my temperature. R, you always know, it's always given, 0.0821. So the only thing I'm looking for is pressure. So we just solve for P, plug it in, and voila, we get 14.2 atmospheres. Okay? So it's really straightforward. Just plug into the formula, whatever I'm given. The whole thing is make sure I'm in the right units. Moles, liters, Kelvin, and the pressure always comes out to atmospheres. Okay? So here's your comprehension check. I have 1 mole. Okay? Now it's at STP. So again, ding, 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 STP, 22.4 liters. Has to be going off in your brain. 22.4 liters. So 13.6 grams, but that's liters per mole at STP. So I know I have to get this to moles. When in doubt, convert to moles. It always helps. Okay? So I'm going to say 13.6 grams. I'm going to convert that to moles. Now, how do we go to moles? Think about how we go to moles. Yes, molar mass. Okay? So the molar mass of nitrogen. So I go to the periodic table and I find nitrogen, but it's N2, so it's going to be times 2. Put the grams on the bottom since grams is on the top. We want them to cancel. Okay? And then, now I need to go, okay, so now I have moles of nitrogen. Well, I want volume of nitrogen. Well, my conversion factor is 1 mole is 22.4 liters. That's my conversion factor. So I just plug that in. Since moles is on top, I put moles onto the bottom. Okay? 22.4, just multiply it out. and you end up getting 10.9. Okay? Now, you can go ahead and try to do this one, okay? Just do it there on your sheet, and then you can go back later and put it onto your Google form on the comprehension check. Okay, all you got to do is put the answer on the Google form. Okay, so go ahead and pause the video, see what you can do on this one. All right, hopefully that was pretty straightforward. Now, on this ideal gas law, okay, with stoichiometry, the whole point of this is that we know our balanced equation tells us that 4 molecules combine with 7 molecules to make 4 molecules and 6 molecules. And let's just assume that this is a G, not an L. That work with this is going to, the ammonia is going to burn and it's going to come off as a gas. I should have put a G there and I put an L. Because it doesn't work, it only works for gas volumes. Liquids and solids don't follow Avogadro's principle, so this would only work if it's a gas. So just assume that that's a gas. So that means that 4 moles of this are going to combine with 7 moles, or 4 molecules combine with 7 molecules to make 4 moles and 6 moles. Okay? Now, here's the new thing. Is because of Avogadro's principle, 4 liters will combine with 7 liters to make 4 liters and 6 liters, assuming that this is a gas. Okay? So the volumes are going to combine in the exact same ratio as the moles, because equal volumes contain the same number of molecules. So if I need 7 to every 4, that means that if I had 7 times the volume, so it can really be any volume unit here. We could be 4 milliliters. It's going to combine with 7 milliliters to make 4 milliliters. It could be 4 quarts combined with 7 quarts. So it doesn't matter what the unit is. Equal volumes contain the same number. So the whole thing is that volumes act the same way as moles. That's what the whole stoichiometry in gases is about. That you can do it either in terms of moles or you can do it in terms of volume. Volumes combine in the same way. Okay? So, how many liters of oxygen then are needed to react with 8 liters of ammonia? Well, 4, okay, combines with 7. Okay? Well, if I have 8 then, I can just use that same, just like I use the mole ratio, I can use the volume ratio, 7 liters for every 4. So I just put 7 liters over 4 here, and then you just end up getting 14 liters. So 4 combines with 7, so 8 is going to combine with 14. It's pretty straightforward. The volume to volume problems are super easy because they combine in the same ratio as the coefficients. So it's really, really quite straightforward. Okay? So, here's your comprehension check number 2. So go ahead and see now, okay, again, how many liters will be formed when 8 liters react. So here's a simple one. So go ahead and solve that on your paper right now, then you can go and put it on your Google Doc a little bit later. Okay, so pause it, do it. Should only take you a couple of seconds. All right, so here's another stoichiometry type problem. But this is a little bit more like a stoichiometry problem that you're used to. So this time we have 100 grams of ammonia. We're doing the exact same reaction, okay? So here's your balanced equation for that. So you have 100 grams of ammonia now, and you want to react, and you're assuming, what's the question asking? According to the reaction, what volume of NO2? So I'm looking for the volume of this. So what I like to do on these, what I like to do is go ahead and just put, remember this is take 2, I already did this one time. Put 100 grams of this right over, this is what I'm given, this is what I'm looking for. And I like to put the gases, like to put the conditions, because I'm at STP. Now at STP, that again, ding, 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 I'm going to use 22.4 somewhere in here, okay? So now if I want to solve for this, okay, I know what I'm given. I'm given 100 grams of this, but I know that for every 4 moles, I'm going to get 4 moles. So I can't do it in terms of grams. I don't have anything grams to liters. I got to go, everything always goes through moles, okay? So I'm just going to have I can just, we already have it down here. We have, okay, this is what we know, 100 grams. We always know the molar mass. If we're given this, we always know the molar mass. And, like I said, we always know 22.4, okay? So, given that, I want to start with 100 grams. That's my given, okay? But I know that I have to convert my 100 grams of ammonia, I have to convert that 2 moles. So I use what? Yep, you got it, the molar mass, okay? So I'm gonna say 1 mole over 17.031 grams, okay? That makes my grams. I knew grams needed to go on the bottom. I needed to divide by 17, so grams would cancel, giving me moles. Now, just like normal, we go to the mole ratio. Well, here's my given, here's my unknown. It's 4 to 4, so that makes it easy. 4 moles of NO2 for every 4 moles of NH3. Now, this is the only part that's different. Now, I want to go to liters, but I'm at STP, so I know I have 22.4 liters for every 1 mole. However many moles, if I have 4 moles times 22.4, so I'm gonna put 22.4 liters over 1 mole. Now I end up having liters of NO2, which is what I'm looking for, so as they say, stick a fork in it because you're done, okay? And so, we're good, okay? Now when you multiply all that out, voila, work it out, just like we just did, and you get 132 liters of NO2, okay? So it's the same stoichiometry, it's just we use the 22.4 as the conversion factor rather than the molar mass, because we're going to liters instead of grams. Everything else is exactly the same as you've been doing before, okay? So again, don't overthink this, don't try to make it more difficult than it needs to be, okay? So here's a problem that you can kind of work out on your own, again, on your paper, try to work that out and see what you can do on that, okay? So, 5.6 liters. It's at STP again, so I know I'm probably gonna be 22.4, okay? So, 5.6 liters, how do I convert that? The first step is always convert to moles. I wanna use 22.4, but this time I'm gonna divide to get my liters to cancel. Then I'm gonna use my mole ratio. And then this time I wanna know how many grams, so I'm gonna go from moles to grams. So I'm gonna use the molar mass of the copper, which I got from the periodic table. And voila, it's a lot of digits there, but we use sig figs. We see we have 2 sig figs here, so we round that to 2 sig figs. Okay? Not too bad, it's just the same exact thing. The only thing that's different is we're using 22.4 to convert liters to moles instead of on the molar mass to go grams to moles. But all the process is still the same. You take the given and convert to moles. All right, so there's your comprehension check. Go ahead and do that on your paper right now. Pause the video, and then just kind of go from there. Okay? All right, let's see if this will go now. All right, more technical difficulties. All of a sudden not advancing. There we go. All right, so you're supposed to stop. You're supposed to go ahead now and go ahead and do your gas law comprehension check number 2 on your Google form, okay? You can do that, and then if you want, if that takes up the full 30 minutes today, you can go ahead and pause the video and then watch the rest of this tomorrow, which you might probably want to do because I have about another 20 minutes or so to finish this PowerPoint up. So if you want, you can just kind of pause it, make sure you get your Google Doc form all submitted. Should have comprehension check 1 and 2 done by now, okay? And then we'll just kind of go from there. All right, so part 3, okay? Part 3, Dalton's law of partial pressures, and then Graham's law. So 2 quick things, not much math with these, but we're gonna get in a little bit of combining this with stoichiometry at the end. So, Dalton's law simply says that in this room right now, it's full of air. Air is not a pure thing, air is a mixture. It's a mixture of, do we know? Do you know? Are you thinking about what is in your head right now? Are you thinking, what is air? I know there's oxygen, because we breathe oxygen. What else is in the air? Hopefully you know, nitrogen's in the air, N2. And it's actually the most abundant. 78% of all the air is nitrogen. Only 21% is oxygen. But what's number 3? We may or may not have talked about it in class. You may or may not have ever heard about it before. Number 3 is kind of a weird one, but it's the noble gas argon. 78% nitrogen, 21% oxygen. 78% nitrogen, 21% oxygen, 0.93% argon, 0.04% carbon dioxide. So all of this together, and then there's 0.03% of other stuff, but all of that together adds up to the whole 100%, all the pressure that the atmosphere is exerting on us, okay? So the total pressure though, pressure is caused, Ms. Michon went over this, but pressure is caused by molecules hitting you. The pressure inside of here is caused by molecules hitting the inside of the balloon, and that's what keeps it up. So the molecules are there. So the more air I put into here, the more pressure there is, the more collisions there are with the container wall, the pressure increases. I have the pressure inside the cleaning duster. Okay, the molecules of the gases in here are hitting the container walls and creating a pressure. Now, I let some out. Now, it doesn't have as many moles in here anymore, so the pressure inside the can went down. There's not as many collisions. Okay, so it's important to understand, pressure is caused by collisions. More moles of gas, more collisions of gas. Okay, so the total pressure is always going to be the sum of the partial pressure. So in the air right here, since 78% of it is nitrogen, 78% of all the molecules hitting my arm right now are nitrogen. So nitrogen's creating or producing 78% of the total amount of pressure. Oxygen is hitting me the most, next, 21%. Only a few argon atoms and even fewer carbon dioxide molecules are hitting me, so their part of the overall pressure is much less because there's many fewer molecules. So the sum of the partial pressures, the partial pressure is simply the part that each gas is going to be exerting, okay? And they're going to exert that whether the other one's there or not. So somehow I could suck all of the nitrogen out of this room. Oxygen's still going to be occupying the whole space. There's still the same number of oxygen molecules. They're still going to be colliding me at the same rate. Their pressure isn't going to change whether the nitrogen's there or not. So the gases all act independently of one another. So, but the partial pressure is just a part of each one. So when we talk about the total pressure, it's the pressure exerted, like in the air, of the nitrogen, plus the pressure exerted by the oxygen, plus the pressure exerted by the argon, plus the pressure exerted by the water, carbon dioxide, and then the pressure exerted by anything else that happens to be in the air. Okay? All together, that adds up to my 1 atmosphere of pressure. Okay? So, I have 4 gases. First gas is that pressure, second one is this one, third one, and fourth. So if I want the total pressure, what do? Bam. I just add them all together. So I get my total pressure. So if all these things were in a balloon or in a container, the total pressure in the container is going to be 926 torr. Now, what we can really deduce from this is because gas 3, the third gas, is exerting 437 torr, there must be more molecules of that gas because it's got the greatest pressure. More moles, more pressure. So really, 437, almost half, and that would be 874 would be if it doubled. So it's a little bit less than half, but most of the molecules in my mixture are going to be this third gas. Okay? This one has the next most. This second gas, that's got the least number of molecules because it's got the lowest pressure. These are your partial pressures. They all add together to get the total pressure. That's what Dalton's law says. Now, Dalton's law, okay, there's your comprehension check. Okay, so go ahead and you can do this. Now, I'll give you a hint. A sample of gas containing 3 gases has a pressure of 1 atmosphere. That's your total pressure right there. So that's the total pressure, and you got 3 gases adding up to that, and you just have to find the pressure of the third gas. So go ahead and pause it and figure that out. That should be a pretty easy one for you to do as well. Okay, now, when we apply Dalton's law, the most important thing we do is when we collect a gas by water displacement. Now, if we collect a gas by water displacement, I'm going to try and do this for you, okay? Let's see here. I'm trying not to break anything. I have some manganese dioxide in this flask, okay? Manganese dioxide will act like a catalyst. This is called a pneumatic trough or a gas collecting trough. It's got a hole where this tube goes into a hole in here, okay? And there's some water in here. And this is called a gas collecting tube, okay? So I'm gonna fill it up with water to the tippy top. You may not be able to see me, I'm not sure I'm in the camera, okay? I'm gonna fill it up. Oh, some spilled out. Gotta fill it up to the tippy top, no air bubbles. Put my thumb over it, turn it upside down in the water. Now again, the water is not coming out of this tube. You should know by now why. This is the same principle as a barometer. The atmosphere is pushing on the water. Water is pushing down on the water. This water level inside this trough would have to rise up for this water to come down. When this water comes down, the water level would rise up. The atmosphere is pushing down and saying, no, it's not gonna happen. So the atmosphere weighs more than the water right now. So the atmosphere is winning and pushing and holding this up. But if I produce some gas and collect the gas can start exerting a pressure and pushing the water down, down. So I have some hydrogen peroxide here, 6% hydrogen peroxide. So I pour this into here and the oxygen begins to be produced and I can collect it here. And you probably cannot see this, but there's bubbles coming up now into my gas collecting tube. That's oxygen gas being produced. Now as the gas builds up in here, it's putting pressure on the surface of this water and it's pushing it down. Okay, so here comes a whole bunch more bubbles coming up, okay? And so it's pushing down, so I'm being able to measure the volume of the gas. Okay, so now it's down to here, okay, now it's coming down to here, now the water level's coming down to here. So we're displacing the water, okay, by collecting the gas, okay, letting it come all the way down. Now, I'm gonna stop it right there, okay? And so we have this. Now I'm assuming that the temperature of the gas is the same temperature as the water. So I know the temperature, okay? Now, normally, okay, what we're gonna try to do is we get the water level to be the same inside and outside. If I could do that, and that's why usually we do it in these big beakers, so we can adjust this, because if I can get the water level to be the same inside, outside, ooh, that's not good for my Chromebook. Ooh. We'll see. Whew. Okay. This is a non-ideal situation. All right, but anyway, if we were to get the water levels to be the same, okay, then the pressure inside would be the same as the atmospheric pressure. So that's what we have to do, because there's no way to us to really know what this pressure is in here because we don't have a pressure gauge or anything. But if we get the water levels the same, the pressure inside and the outside are the same, so we can use atmospheric pressure. Now, here's where Dalton's law comes in. This isn't just going to be oxygen gas up here now. Okay, the water level's right there. Everything above here, some of this water, as the gas is bubbling through, some of the water evaporates. That's that water vapor pressure. So the water evaporates and occupies this. So some of the pressure is due to water vapor, not just due to the oxygen that we collected. So we only want the pressure of the oxygen. We want the partial pressure of oxygen, not the total pressure. So we have to then subtract out the water vapor, okay? And you can get that value from a table. Now this is in the back of your book or whatever, so we assume, let's just say we're at 20 degrees in here, the vapor pressure is going to be 17.5. So 17.5 millimeters per mercury of the total pressure inside of here is due to water, not due to the oxygen, okay? So I'm going to try and move this out of the way so I don't spill it anymore. Okay, put this up into here. Try and move this. There we go. All right. So, when you have a gas collected by water displacement, the gas comes in here, the water gets pushed down, but we're going to have a mixture up here of the gas that we're collecting, the hydrogen gas, plus water vapor, because water just naturally evaporates. when the levels are the same, the atmospheric pressure is pushing down with the same force that the hydrogen and water are pushing down. So the pressure inside this is going to be the same as atmospheric pressure. So if I want to go and I want to find what the pressure of the dry gas is, I just get the atmospheric pressure for the day. I usually just go online and say, hey Siri, what's atmospheric pressure in Hoover, Alabama today? And then we can subtract out the water vapor pressure from that table, and that gives me the pressure of the actual gas on the inside. Okay? So, as an example, if we collected gas by water displacement, now this is always your key, this phrase right there. So if you, hopefully you printed these out or you have this, you need to highlight that, because when it's water displacement, that tells me I have to subtract out water vapor pressure. Okay? All right. So, what was the pressure, partial pressure of the oxygen gas collected? So I just want oxygen gas, I don't want the total pressure. So I have to go through. But the atmospheric pressure is 731. But part of that, the partial pressure of water, the water vapor pressure at 20 is 17.5. Therefore, the pressure of the dry gas is going to be 713. Okay? So that's going to be an extra step. When you collect it by water displacement, you have to subtract out water vapor pressure. That's due to Dalton's law. Okay? So, here's another one. Okay, so we collect the gas, but the temperature's 27. Okay, it's not STP, we're at 743, but again, collected over water. So that's going to tell me I have to subtract out water vapor pressure. Okay, so, did you get that? Okay, you're supposed to kind of do that. I was supposed to tell you to pause. There's your answer. See if you can do that and get that answer. Okay? Let's see. All right, so let's just see how you worked it, if you got this. So we can just say, a student collected 100 milliliters of neon gas over water when the temperature, so I know the temperature is equal to 27 degrees Celsius, which we add 273. So that's going to be 300 K. So that's my temperature. Okay. The volume is equal to 100 milliliters, but I know I need to convert that. I'm going to just go ahead and make that liters. Okay. If the barometer, so the pressure of the atmosphere, is equal to 743.3 millimeters of mercury, okay, but I need to subtract out water because not all of that pressure is due to the neon gas because it's collected over water. So I have to know what the water vapor pressure is at 27. So I'm going to go back to 27 degrees, and it's 26.7. Okay? So 26.7. Okay? So it's going to be minus the 26.7 millimeters of mercury right here. So when we do 743.3 minus 26.7, I've got water all over this one too, comes out to 713.6 millimeters of mercury. But what unit does pressure have to be in to use the ideal gas law? Ding, ding, ding. Atmospheres. So we're going to go 713.6 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury. That's going to give me my pressure. So I just divide this by 760 of 0.939 atmospheres. So there's a little bit of work just getting the right units. You got to take your temperature, you got to get it to Kelvin, you got to use your volume to liters, pressure, you got to subtract out your water vapor pressure, and you have to then convert it to atmospheres. But now we can go, what is the pressure? Okay, well the reality is that I didn't need to do all of that. What I want to figure out, I'm going to do another part to this. Okay, our pressure is going to be 0.939 atmospheres. What is the pressure of the gas, or 713.6? Is that even just double check, 716 points, did I subtract wrong? 743.3 minus 26.7, I get 7, I needed to put my glasses on. I think I did it backwards. It's 716.6, not 713. Which means, divided by 760.943. All right, so let's just take this one step further and say that, okay, I now know that's how I calculate my pressure, but now I know the temperature, I know the volume, I know the pressure. I can calculate how many moles of gas, moles of neon, because PV equals nRT, N is going to equal PV over RT. So I can take my pressure of my dry gas, 0.943 atmospheres. I know the volume is 0.1 liter. R is always 0.0821, and the temperature is 300 K. So I put all of that in, so I would know that in my 100 milliliters, this is a way for us to be able to get moles. We have times 0.1 divided by 0.0821 divided by, and you end up getting 0.00383. So the ideal gas law gives us a chance, a way to know how many moles, how many molecules are actually present in our mixture, if we know the temperature, the pressure, and the volume. Okay? But the key is when you collect a gas by water displacement, you have to subtract out the water vapor pressure. That's all the key about Dalton's law. Let me bring this back. All right. This question only asked for the pressure, which you only had to subtract, but in knowing all of these other things, we can also calculate moles using PV equals nRT. All right, now, here's one for advanced level, okay? But notice on this one, notice how it's different on this. We're given a volume, a temperature, and a pressure, but now it says what's the new volume of the dry gas at STP. So now I have a second set of conditions. STP, 0 degrees Celsius, 1 atmosphere, or 760 torr. Okay, and so I have 770, 760, I have 23, I have 0. So this one tells me, okay, I'm going to have to use the combined gas law because I have all of those conditions, okay? So we just plug in. Now the only thing you have to make sure you do is subtract out water vapor pressure again to get that. So you just plug in and voila, you just use combined gas law and you get it, okay? Pretty straightforward. Again, collected over water. The key is I have to subtract it out. All right, 49.1. Lastly, and even more difficult, okay? So, here's a normal stoichiometry problem. I'm given this stuff. $5 grams of this, and I want to know what volume, X liters of this, but it's at 20 degrees Celsius and 800 millimeters of mercury. So it's not at STP, so I can't use 22.4, okay? Think about that for a second. I'm going to check the video. Okay. Well, we always know we have to start with the given. 5 grams, KClO3. Okay? Well, 5 grams of KClO3, the first step of any stoichiometry problem is take the given and convert it to what? Yep, moles. So I'm going to say 1 mole over the 122.6 grams. That's the molar mass. So that tells me how many moles of this I have. Now, once I have that, I need to know how many moles of oxygen. So now I'm going to use my mole ratio again, 3 moles of oxygen for every 2 moles KClO3. Now, this is where it's a little bit different. Normally, we'd want to, if we was at SDP, we could use 22.4. If we wanted grams of oxygen produced, we use the molar mass. But we need to know the volume, but not at STP. We have to use the ideal gas law for that. So I have to figure out how many moles I have. So I just plug this in, 5 divided by 122.6 times 3 divided by 2 equals point, I don't think I did that right. Ooh, I'm having a rough day. I'm getting a different number than what I did on the calculation. Why is that? Point 103? Let's see. Hold on a second. Making this real life here. Okay? No, let's see. Oh, here we go. It's down here. I was getting confused. Okay, so I got to make sure that that number is right on there. I'm getting a different number. I'm going to do it one more time. 5 divided by 122.6 times 3 divided by 2 equals. Ooh, when I did that before, I got a different answer. Okay? So we're going to ignore that. So on the PowerPoint, it's wrong. Okay? So I'll come back and fix that. But this comes out to point, I'm going to go back, get rid of all that. Get rid of D. Okay? 0.0612 moles of O2. Okay? So, 0.0612 moles of O2. I guess this is what happens when you're trying to solve these problems sitting in a recliner watching TV rather than being at school. Okay? And we all have to adjust here to a different learning environment. So that's how many moles of oxygen I have, but I need to know liters at these conditions. So now this is where I'm going to plug in. Now, we have to look at all these different things. Pressure. The total pressure is 800 millimeters of mercury. But I have to subtract out water vapor pressure. At 20 degrees, we already said it was 17.5 millimeters of mercury. Okay? So that tells me that we're at 700, and let me see if I can do mental math here, 782.5 millimeters of mercury. But I know that I need to have that in atmospheres. So I'm going to have to divide by 760, and that's going to give me how many atmospheres I have. 782.5 divided by 760 is 1.03 atmospheres. Okay? So, once I have all of that, temperature, we add 273, the temperature is going to be equal to 293 degrees K. So now I can plug it in, and I'm looking for volume, so PV is equal to nRT, so volume is equal to nRT over P. So we just plug in everything that we have now, 0.0612 moles, 0.0821, temperature of 293 K, and the pressure, 1.03 atmospheres. Plug all that in. I told you it was a little bit more difficult. A little more steps. Just combining everything all together. 0.0612 times 0.0821 times 293 divided by 1.03 equals 1.43 liters. Of oxygen. So that's what we could expect to collect at 800, at 20 degrees, the total pressure being 800 millimeters of mercury, we should be able to get about 1.43 liters of oxygen. Now, again, PowerPoint answer is wrong, unless I change it before we posted it. I'm not sure if it's posted yet or not. But anyway, I'm going to go through and correct it if not. Okay? So, that's a complicated problem. That's stoichiometry. This is the only time you can't do the stoichiometry in all in one step. You have to break it up into two. Okay? So, that's a good, challenging problem for you. If you're in regular chemistry, you can just kind of go right on past. You're not going to have to be able to do those. Okay? So here's my solution for it, but this solution is wrong as of right now. It's all down here. So I got 7.14, but my moles is somehow or other. This is all set up right. It's just that number right there that's wrong. I got to change that one. So, all right, last thing. And if you need to, you can pause the video here. I don't know how long we've been going today. If we're over the 30 minutes and all that, then just go ahead and start playing this tomorrow, and then just kind of go from there. But we'll only have a little bit left on this. Okay, diffusion and effusion. Diffusion is just the natural spreading out of a gas one through another. We know that all molecules are in continuous rapid random motion, kinetic molecular theory. Okay, so if I was to spray this right here, that gas is slowly just going to spread out through the whole room. That's the diffusion. Now it's very logical. Which molecules do you think are going to diffuse faster? Small light ones or heavy bulky ones? That's pretty much a no-brainer. Small light ones are going to go faster. I always say this, if you have a big mass, you ain't going fast, okay? If you have a big mass, you ain't going fast. So, you know, your sprinters don't look like me, okay? Sprinters are small and skinny. If you have a big mass, you ain't going fast. So smaller molecules spread out faster than bigger molecules, okay? So diffusion is just the spreading out. Effusion, it's the escape of molecules through tiny pores. Now I blew this balloon up today, okay? This is a latex balloon. It actually has little tiny pores in it. The molecules can barely fit through. This has been sitting here for a couple of weeks. And so this doesn't have a hole in it, but what's happened is the air molecules, the oxygen and the nitrogen, slowly made it through the little tiny openings. And so little by little, they're effusing out. Now again, this makes total sense. Which one's going to get through the tiny opening faster? The small skinny one or the big heavier one? Well, of course, the smaller one is going to get through faster. Okay? So, the gases at the same temperature and pressure are inversely proportional to the square root of the molar mass. We can really just talk about molar mass. Okay? Here's the key thing. Lighter molecules move faster than heavier ones. Duh. Okay? That's why sports cars are small and light. Okay? So, which one would effuse faster? Which one's going to get through the holes easier? The tiny one or the big one? Well, obviously, the one with the lower molar mass, the tinier molecule, is the one that's going to get through faster. Okay? So that's all you really need to know on diffusion. You need to know the definition of that, and you need to know that lighter molecules are going to diffuse and effuse faster than heavier molecules. Okay? So this is a pretty straightforward comprehension check. You can just do that. You can just circle it. It's pretty easy to know. Remember, the molar mass is kind of the hint to do that whole thing. All right, so that's it. So go ahead and do your last Google form, Comprehension Check 3. Get that turned in. That's for today and tomorrow. That's your assignment on that. And then I will see you again next time when we start talking about, so actually we're going to go over, give you some practice problems on that, and I'll kind of work through those practice problems with you before we go to the test on this stuff. All right? Happy virtual learning.